Okay, folks, let's get started. So it's my pleasure to welcome Professor Pingsha Dong to deliver today's CNRE winter seminar. Professor Dong is the Robert F. Beck Collegiate Professor of Engineering in NAMI and is an expert in the computational modeling of fatigue and fracture, welding, joining, and metal additive manufacturing processes. He's especially known for developing a very widely used method to compute structural stresses resulting from fatigue and fracture in welded structures. Professor Dong has received he's graduated a number of students, published a large number of papers, and received a large number of awards, of which I will mention a couple here. Those being the AWS Comfort Adams Lecture Award and the SNAMI Helmer 8L Han Awards. And this he received twice. And these are just two of the many awards that he's received. So I'm really looking forward to your talk today, Pingsha, and thank you very much for taking the time to speak to us.
Thank you very much, Mahesh. I think my audio is okay if I stand here, right?
Yes.
Okay. Thank you for coming over, because actually it took me a while to find how to locate this particular location, even if when I come out to the fourth floor. So again, some of you have attended my previous talk on similar topic. But today I want to select a more general topic, cover a broader area, and then later on, if there are interest, I can explain or provide additional detail if needed. If you want to cover broader interest. So the title I gave a little shorter than what is emailed out. I'll call it enabling next generation naval structures through smart construction. So in our original title is smart modular fabrication and assembly, meaning the same, essentially same thing. With that, I think just need to go back and forth a couple of times. Okay. So here's what I plan to do. First, give a brief introduction of our group, we call Weld Structures Lab, and talk about some of the general activities, both from fundamental research to engineering applications, and then try to zoom in on some of the shipbuilding challenges we are facing, both on the commercial side and also on the government side or defense side. I think the key element, key thread throughout the presentation is smart modular construction. And I'll define what I mean, because today we talk about the construction 4.0, industry 4.0, and smart modular construction is part of that element, is one element of that. Actually, this is not just using, say, cyber, AI, all this sensoring, autonomous systems. I'll be focusing on, at least from the area I'm getting into, is a look at how to understand the underlying mechanics, physics, and then generalize from that, come out with reduced order modeling, so we can integrate through multiple disciplines to come out with an engineering solution. In the end, come down. With that, I also just share with you a little bit on the multi-material structure concepts and some of the challenges, also some new opportunities, which can be pretty exciting when we, if we can overcome some of the challenges. So with a quick conclusion. With that, this the two charts, how I describe my group in terms of some of the from fundamental research all the way to engineering applications. Our group this, I call it integrated smart design for construction and the structural performance modeling in the fusion-based processes. So this is a pretty busy chart because I keep adding them in, adding new element in. Oh, this is over a period of 25 years, supported by both industry and government over 25 years period. So starting from the top, we look at how material interact with processes that can be laser process, can be electron beam process, can be any traditional arc welding or thermal cutting or any localized heating cooling processes. I call it the prior operation related to how material get made, particularly when we deal with sheet and plates. and how that material under given condition interact with the processes that I can refer them as a thermomechanical process. And, that means could be local heating effect, whirlpool penetration, the dynamics of the whirlpool surface for control purpose. In the end, related mechanics, that's pretty much implemented as an Abacus special subroutine, talk about from a high temperature all the way to room temperature, how material interact with the heating cooling process of either weldability or not modeling or thermomechanical modeling. In between, we can look at some of the microstructure, metallurgical impact, how they impact property development. In the end, what will be the defect formation mechanism, how those defects based on their characteristics impact structural performance. Recently, we add 3D printing because that rapid qualification and certification has been very challenging, particularly for defense side of the application. So how to quantitatively demonstrate distributed effect, how they impact structural performance, and then talk about thermomechanical deformation, reduce stress distortion development. So this is a pretty bird's eye view of what we do as a group over more than 2 decades. On the right-hand side, look at how reduced stress distortion develop, how they will impact property. So again, this is not just nice, those are the not the cartoons that are part of the research programs and as the illustration of the key results. So the intention is from engineering application side, those understanding established will enable us to provide guidance, how to certify a given component, how to quantify that component will perform to the expectation, right, from designer point of view. So that's a fusion process. And the second chart is the last one to describe my group. We're dealing with more fusion, solid state processes, and they're dealing with the multi-physics-based modeling from processes that could be induction, could be electrothermal generation, and the mechanical coupled process. And as indicated in the chart, we don't develop from everything from develop tools from ground zero, ground up. We take advantage of what is available today, and then develop those unique functionality, integrate with the existing software packages available in the marketplace that will facilitate technology transfer. So again, a moment ago, I forgot to mention every red color are the unique computational modules, and everything with the star already implemented or deployed by commercial software companies, particularly 3DS, and also VFT, and the Caterpillar is a part of that process, some of the tools development. More recent development, we look at some of the new techniques, and some of my students are part of that development team. So anyway, this on solid state process, quite a bit of activities recently. I think later on I'm going to highlight actually when material very incompatible, but when you consider very unique thermomechanical condition, also metallurgical element, from material science point of view, we can induce molecular level bonding. Those type of phenomena we don't fully understand. So I'm working with a number of faculty members across colleges to provide more foundational type of knowledge to further advance those methodologies. That including the plastic to metal or thermoplastic polymer bound with the metal directly at a molecular level, both experimentally validated, also from computational molecular dynamics modeling, with the IU equivocally demonstrate indeed a particular bond can be identified even under ideal conditions. So without dealing with the controversy, we had to justify if there's contamination in our observation samples. Some of the 3D solid state printing process, we call soft packet AM. We can deposit similar material, dissimilar material on the substrate, and by using a novel extrusion process, and that's already patented, licensed to a number of companies, and that enable us to look at aluminum with steel deposition, copper, aluminum to copper for battery-related applications. So there are many possibilities. One key thing here is The reason I mentioned some of the phenomena not fully understand, for example, we consider aluminum to steel. This is a classical problem people have been struggling for the last 70 years. Because they form intermetallics, very brittle, they can crack up immediately after welding, after putting together. But if you induce a strain rate to such an extent that produce a shear localization process that can become adiabatic, and the self-energizing mechanism, the strain rate effect has significantly by 2 order or 3 order magnitude reduce that transition zone between steel and aluminum alloy. So this is what this chart tries to show. Actually, we can replicate that in our experimental setting and demonstrate that sample is very strong, also corrosion resistant. Later I'll get into that a little bit. So those are the nitty-gritty details. We do a lot of things. Actually, I try to motivate students who interact with me, say we don't want to forget a bigger picture. Okay. So the bigger picture from those nitty-gritty details lead to say we want a quality of life is important for naval architecture marine engineering. Obviously, the spring break coming up, so that's something you might want to consider. Okay. National security, a lot of discussions by this department of the Mahesh group. And obviously, we talk about Virginia class and Columbia class submarines. The difficulty to meet national security demands. Right. Energy security continue to be important. Obviously, LNG. So I'm showing in my 461 class, I use the same picture. It's a prelude that's still, I think, the largest floating structure built on the commercial side. Okay, some new just news clip. So actually, all these things we talk about, we have a context. They are supporting the producibility, the structural performance, and the impact on environment. So that's just come back to one point. So now all this, let's zoom in a little bit. Say what I mean by smart construction. Actually, modular construction is not new. That's back to Henry Ford days, in Detroit. That's what the people do, but you have about 100 years to iterate, figure out what is the best way to do it. You have a complete supply chain nearby. They're producing tooling, they produce automation algorithm to support OEMs, assembly, design, and the entire manufacturing processes. Aircraft dealing with a similar thing, modular assembly, modular manufacturing, but the price point is very different from ship structures, right? And also they have every incentive, just like us, want to simplify the process, reduce cost without sacrificing performance. Ship structure, actually from the US shipbuilding point of view, we are still in the early 1990s, late 1980s. This is the chart presented to Avondale, I think in the beginning of 1990, say how to achieve modular construction for ship structure, because we're dealing with a very unique product. That is the sort of a Bible every shipyard try to introduce to their production process. So now what is missing here is, all this look good, makes sense, but doesn't have the mechanics underpinning, the physics underpinning, supporting how to go about, how about before each unit, what I should do. At the unit level, now we can follow IHI, Ishikawa, Jima, and back in the 90s, transfer technology to the US. That technology, I call it a group technology, and you can read the entire book, but I simply summarize that in simple way, essentially 2 items. Similarity in interim product forms. Interim product here, I define everything in between lead to a given identifiable module. Every step of the way, you have to have a certain principle imposed. So far, the Japanese 1980s had a tremendous success, but we have not been able to introduce much change, particularly for shipbuilding industry. So those group technology concept, group interim products based on similarity in product form, similarity in processes. Those are conceptual, cannot be acted upon by physical principles. So you can translate that, you and I come to similar conclusion, right? They also relate to a shipyard manufacturer's capability. So what is missing is the three things. That similarity all good at one particular stage called manufacturing cell or family manufacturing processes, like how they will interact with the downstream process at the upstream, what should be the consideration. And then how that downstream, upstream interact, contributing to the final quality and also from performance aspects, if they satisfy all the criteria. And also, most importantly, lack of physics or engineering principle, so people can articulate or implement on different variations of the interim product. So that's what is missing. Actually, here is how I frame Industry 4.0, particularly in terms of construction 1.0. Here, the word construction, I try to emphasize small volume batch production. That means we are in this regime, either project-based or batch production-based. So when we talk about the Virginia class or Columbia class, we are somewhere in between the lower right corner. Doesn't matter what products you are dealing with, the entire manufacturing industry, we want to move to the right-hand side on the horizontal axis. That means we want to have a part commonality so we can automate. Digitalization today in the Industry 4.0, not just have robotics, have computers. That means you have to have a pattern defined so that you can group things effectively together, and then you can automate based on certain criteria. So digitalization is important. To achieve that, when we deal with one aircraft carrier or two aircraft carrier or a couple of submarines, we don't have the volume. So what do we do? Here is the red color. That means you have to divide, combine, and finally conquer through a smart modular design construction concept, which I'm going to elaborate. Only then you can come down to, at a piece part level, all the way to final unit or final block. Once we figure out what is the product family definition, and then we can automate. So digitalization covers everything. Say how to achieve that volume, that repetitiveness, that commonality when we don't have unique identical parts, right? That means we're based on similarity, based on additional principles. So that means what this says is there's quite a bit of work need to be done, okay? And then you go this U shape, and then we can automate. The commercial side, particularly overseas shipbuilding industry, doing very well. They are facing similar issues, but they're willing to devote resources and take advantage of new technology, working on this part, diagonally go up or right? Whoever can do it better will be competitive, will be the winner, particularly in today's competitive marketplace, even on the commercial side. To do that, without getting into detail, the two flow charts I showed earlier, based on the physics, mechanics, understanding the entire process of the manufacturing construction flow, we come out with 5S principle. Again, some of you are already familiar with that when you take my courses. We borrow what is group technology going to offer, similarity in product form, similarity in processes. The mechanics underpinning, again, for lack of better description, some of you may have different suggestions. We're going to have a symmetry in geometry, symmetry in processes, and the stability in shape, and the supportability. To give you an example, I deal with this particular shipyard, one of the major shipyards in the US. This one satisfies two similarity requirements. They're going to build more than 100 of those. Every piece is slightly different, but looks similar. But the dimensional accuracy is very important when we do modular assembly. Now, this is supposed to be flat. The vertical is supposed to be vertical. They do not satisfy all these requirements. So for naval architecture, marine engineering department student, when you do a summer internship, keep this in mind when you tour shipyard, okay? You continue to see that. That satisfies the Japanese group technology concept. But in my view, based on this criteria, that's a worst case scenario because no symmetry, right? No symmetry, no stability. Stability means that component, that module, that interim product can maintain shape even upon disturbance. Handling, when you work on it, it doesn't have stability. Naturally, they're going to bend or develop curve. That's a very bad interim product. If you don't have a symmetry, you need to have a stability. If you don't have stability, you have to be able to support it. That means by design, each step of the way, the design engineer, production engineer need to have an idea how I'm going to support this if I don't satisfy those stability symmetry requirements. So this is a box beam. This one is much easier. Industry tend to do it quite a bit when you drive on US 23, where that just came from. The semi truck or the longitudinal rail is a C frame. That's exactly what this type. This one is worst because the weld location, the seam location, the plate and U shape is not has no symmetry with respect to XX, even though it has symmetry YY. By definition, you don't need a computer simulation. That longitudinal rail could develop both just by design. There's no way to mitigate that. Okay. To overcome that, we also need XX symmetry and YY symmetry. So this is better. This one is the best from performance point of view, which I'm gonna get into, not gonna get into in detail. So what this says is just symmetry, just similarity, not good enough. That's what the Japanese offered. And we have not advanced that concept since 1990s. Okay, so that's the message.
So when you say symmetry is needed, that's you're saying if the welds are symmetric, then can make the general scheme overall is better from a structural perspective. That's
so both design. The designer can decide if they're going to use 2U or one flat plate by a single U, right? So that's a design engineer, manufacturing engineer, all have to say it. But today, design engineer never care about how this get built. Okay, I may be too strong a word there. Okay, you put that drawing together, they build it. Right? In that case, the designer, people consider that they can consider it 2U shape. That gave us very nice product family definition because you have to deal with 1U many times. And then you can assemble them, give you both symmetry, and by definition, they going to give you superb product. And this one is fast. Again, sometimes we may not have that choice, and then we have to compromise. But when you compromise, you have to have a target. What is the ideal situation? So with that, let me define a few things to show you some examples. Some of the examples should be look familiar to you. So when we do thermal cutting, later I'm going to share with you some examples. This is a big plate. If I want to cut precision 28 inch by 48 inch. So what is the symmetry definition in processes? The plate come in actually has a reduced stress distribution because plastic is only located on two edges. By definition, they tend to be symmetric, just like the geometric symmetry. That means reduced stress distribution symmetry happen to be coinciding with plate longitudinal axis. Okay. So now today, when we do CNC programming, when you go to panel line, cutting line to shipyard, they always start from a lower right corner because that's the CNC reference position and cutting things horizontally. Piece one, piece two, you can see both the part distorted, the part get cut out, distorted, and also the overall plate start moving. If you visit shipyard, they call plate walking, physically walking. You cannot stop it. Okay. So actually, without investing any equipment, that's why it's called smart. That means if you know what is governing that deformation process, to achieve approximate symmetry, cut first piece. That means I introduce some disturbance to the existing reduced stress in the plate. Next one should be on the upper left corner, and then that should correct things. Okay. So that case, one-to-one comparison with a scale of 30, what do we see as a drastic improvement? Without introducing any new equipment, any new procedure, except just different programming on the CNC side. So that's we call it. One is asymmetrical with respect to the reduced stress distribution, one is symmetrical, but obviously by definition, we should know if a simultaneous cutting would be even better, right? So anyway, this is pretty recent. This is from East Coast. Without mentioning name, I said they have cutting distortion problem when they deal with HLSA 100 high strength steel. The higher the strength, the higher the reduced stress, and the situation becomes worse. I asked them to send me their CNC scanning path, the cutting path, plate 1, plate 2, just opposite to what we talked about. They are still doing that today. Only one small shipyard implemented this symmetry concept. The rest of them still working their conventional way. I asked them, one of the major shipyards, why you want to do that? Say, need $2 million to do reprogramming of the CNC tape. That's how, that's not just technological, that's how business practice over the years become a culture issue, right? They cannot do reprogramming. Another plate, cut plate 1, plate 2, plate 3. So the argument is I want to make a best of use of material. Actually, you can cut plate 1, cut plate 2 on top, cut plate 3 in the same location without introducing any additional material with waste, right? But that will give a better result. So anyway, that's just an example. Say what do I mean by smart? That means understanding a little bit about the physics. Here's the example I use quite a bit. This is from Avondale and published in a SNAMI paper almost 10 years ago. So again, I keep teaching our student when you do design, actually 20 minutes for a designer to put the insert plate with a different color other than yellow. That means Navy has a requirement because the stress is high. If the stress is high, you use a mouse, you circle that area, right click, say thickness increasing from 5 mm to 10, 12, 15, up to 20 for this particular case. Pretty casual process, 20 minutes. After 1 week welding to put this piece together, they have trouble to put a stiffener on. Another 2 weeks, cut pieces out, re-weld them, manage to put a stiffener on. They will ship, they shipped this immediately outside the panel line. They don't want to look at it again. Let somebody else worry about it. So actually, designer has everything to be blamed here. You should not, that insert plate should be very careful. If you have to use it, the shape, the location has to be carefully designed, right? For this particular case, that's the example causing all this problem. This is not just the accuracy. So that's still happening today. Okay. Question? Yes.
Picture on the right is what happens when the blue panels are actually welded in.
Yeah.
The yellow.
That's right. And because of the high stiffness interaction, they just buckle. Right? Actually, as soon as you drop this thick one in, actually one of the session in 461, I asked student to do exact experiment, cut a piece of paper with a hole, and then cut another cardboard piece with the exact dimension. Put the cardboard piece into a piece of paper, you know the paper going to wrinkle. You don't have to do anything to it because that's an implant stiffness mismatch. This is still happening. Okay, this Navy's rules require you have to reduce stress locally when you have equipment or weapon systems, and they don't want you to use any other design scenario. So that's one situation we have to mitigate. The criteria is based on 1950s technology or understanding. So now, sometimes we don't have symmetry because by definition, ship structure is very complex. So here I'm using an example to illustrate when you weld a T-stiffener, this background to look at the titanium. Because the titanium extrusion is very expensive, we had to use called fabricated stiffener, T-stiffener. So anyway, you type them together, you put this weld together, you develop, measure from the flat surface 5.8 millimeter, 7.5, 8.3, that's already out of whack. You know, imagine you're going to do 20 feet. So that means if you don't have a symmetry, you have a problem. That problem has to be mitigated by smart fixturing. That need supportability, and then you have to accomplish that stability by using additional means. Right? So that case, we can use proper fixturing, which means provide clamping. Clamping has to be positioned in such a way produce uniform load distribution as close as possible to the action zone. Action zone is the plastic zone. Plastic zone located at the intersection. That means you want to be as close as possible. Too close interfere with the assembly process, so you had to compromise, right? So that case, for illustration purpose, using computer model, we can demonstrate just doing this, you get a very significant reduction, 0.7, 0.9, 2.2. This get validated by measurements. So during this process, actually we asked, say, for this particular case, you had to use clamping. Then on the phone back then, we don't do Zoom often. There's no Zooms. Say, yes, Dr. Dong, we clamp, we tie down. And now we see what happened. Remember, we talked about supportability. This bottom doesn't have enough support to give you a reference surface. The base plate, before you put a stiffener on, reacting to that local big rock, right, loading. This curvature solely due to the position of this block, and because producing local elastic deformation. That get welded into the stiffener, and then we blame, say, the welding process, too much heat input. Right? So actually today, the inaccuracy problem, not just one particular process, it's the entire system lack of process definition. So this doesn't have supportability, doesn't have a symmetry, and then you need to have proper fixturing. Right? So that can be, you can still use this, but you can manage to put a load distributed with a heavy beam, with the bottom shoe support, which is, I think in my 461 class, I have a number of examples demonstrated by shipyard. So that means when we say clamping, fixturing, not just putting heavy weight on it, where you position them. Where you position them, the pairs of physics coming in. The reason you produce that deformation, asymmetric deformation due to geometric asymmetry is the plastic zone, called shrinkage zone. And if we look at the T stiffener, L stiffener, and on cooling is producing natural shrinkage reaction. That shrinkage reaction only occurred within this plastic zone neighborhood. Rest of them, if you plot this deformation from the bottom surface, what you see immediately, just like when you open the door hinge is the plastic zone, it's gray color. Rest of the door is a rigid body rotating. That means if I do any clamping here, that doesn't do any good. Elastic deformation, fully recoverable. During welding, everything looks reasonable. As soon as you release it, they pop back, right? The only way for that to occur is to put a clamp down only vertically as close as possible in this neighborhood. Right? So it doesn't matter what steel, aluminum alloy, titanium you are dealing with. The magnitude varies, depends on material property, but the trend is identical. That means same methodology can be used for different material, different structural elements. To demonstrate that, here's the example. It's a shop floor example. This particular is a supplier manufacturing shop willing to invest. Anytime you talk about clamps, they will clamp things down nicely. They have heavy floor. They can put a bolt, that's a connection device. So this violates what I just said earlier. That means if I clamp things down, naturally they have an elastic reaction. The elastic reaction is recoverable, right? This should not do any good. After that, same angular rotation. Right? So that's violating the existing criteria and doesn't work, even though you're willing to use a point clamp rather than this big giant rock, right? Yeah. Actually, how to do that? One particular company is very interested. Actually, they look at it and say, when we explain, you had to move things closer, and they tried. This is the clamp coming down when they weld this particular weld. Now everything released. This still indicating virtually flat versus this particular case. Okay, actually, so that's That means not just simply tie things down. You have to know where to work with, right? What position, what manner you're going to apply to achieve that supportability and the shape stability. So again, when we deal with the realistic marine structures, sometimes you have to deal with the funny design features. A lot of the time we don't have much control. This one we call complex panel. We tested in one major shipyard. This part has a 10 mm insert, rest of them is 5 mm with T stiffener. Obviously, by definition, no symmetry. They put the bottom wall together, put two plates, and then assemble stiffen. Actually, when we run into this situation, we talk about divide, combine, and conquer. That means if you don't have an opportunity to change the design, when somebody gave you this design, what we can do is let's isolate the part doesn't offer symmetry, add a lot of complication. That means don't weld this weld first. First deal with the two halves. Bottom half symmetry, top half you require special tooling. You're gonna weld thousands of those, right? And then that gave you the volume, the repetitiveness to build your knowledge, your expertise. And then you come back, tack stiffener, gave you the stability, finish tacking, and then once both sides get welded with the stiffener attached, and then you weld this weld. Right? So back then, LADAR is not that sophisticated. It's about more than a dozen years ago. This is about 2 inches out of plane distortion. This is about less than half. So that's the improvement. Again, we are not introducing any new equipment except changing the flow, workflow by defining interim product differently based on those physical attributes. I call it a 5S principle. Right? So that means we don't always need everything's ideal. As long as you know the principle, you can apply them properly. Again, talk to most of the US shipyard today, except one, and changed. And if you ask them to put the 8 stiffener together, they always starting from one side. Actually, one particular shipyard follow a river flow direction. Say historically, they follow the river, upstream, downstream. So you assume this upstream, go downstream, assemble all 8 stiffener. We demonstrate with the computer model every now and then. Say, let's demonstrate. The residual stress become very unequal, unsymmetrically distributed, which is very bad for buckling. Stiffener 1, stiffener 2, you can see the blue color is compressive residual stress get built up and unsymmetrically with respect to the neutral axis of the panel. If you do center out, 1, 2, 3, 4, 5, 6, 7, 8, you get about 3 times the buckling resistance versus the conventional procedure. Again, we demonstrate that with the actual production line by designing what we call test panel that's a 16 by 20 feet size, using conventional method, inside out, almost virtually nothing, right? And then we can also use the reverse arching, stretching the plastic zone, the shrinkage zone, without getting into detail, almost all gone, satisfy all requirements, except by that time, because when we do reverse arching, we bought this 2x4 wood block from a Home Depot near the shipyard. By that time, the 2x4 wood cannot support it anymore, collapsed. Okay, this part caused some damage. Otherwise, this panel is perfect from their dimensional accuracy acceptance criteria point of view. So now, when we talk about symmetry, this is a chart I used in Virginia Beach. And one time I get invited to give a keynote lecture on automation. And they wanted me to talk about automation. So actually, I showed them 5S principle. In the end, I conclude that best symmetry is simultaneous. Actually, that back then, Japanese, this is where the picture coming from. They can weld 8 stiffener, 16 torches. That means each stiffener has a two-sided weld simultaneously, hacking, finish welding. So that's the best mathematical symmetry. Okay. No US shipyard I know of weld more than 2 stiffeners simultaneously based on pre-COVID knowledge, unless things change. The Japanese, 15 years ago. So now other industry related industry is related to Generation 3 nuclear reactor protection shield. The story is that we want to do modular construction. modular assembly, go to power plant, assemble this together. They're gonna build thousands of those units. This cross section is about 16 feet or 14 feet, gonna be 70 feet long into the paper. They're gonna build thousands of this, ship to Florida and South Carolina. Everything's good on paper. Okay. And then they say how to do the modular construction, modular design. So let's visit shipyards. They visit all US shipyards. So now you know what happened, right? Okay. Shipyard tell them, say, there's peers of how we do things. They did not tell them the problem they run into. So they built first markup. This markup not 70 feet into the paper, is about 25. So now plus minus 3 mm over the entire length. So you can see this out of whack already. It's supposed to be squared album. Okay, you don't need to do measurement. Actually, I think in my class I have a better picture. They invited me to the shop floor, try to do measurements. So you don't need to do measurements. And I already know the problem. And say, doctor, can you help us develop optimum welding sequence? I said, I want to be honest with you. Nobody can fix this problem. Okay. That's because the design is bad. Okay. Again, for those of you who took my course, keep quiet. I asked her. We were you're not taking my class yet. I'm not taking. What's wrong with this design? Ship designer, symmetry. Definitely no symmetry. What else? It's not the supported shape. What is bad support? That's bad support also. That's still one key element missing. Rotational stiffness. This thing start rotating. Okay. So in ship structure, how you deal with rotational stiffness, we call, what is that? Web frame, right? Web frame. Is that correct? Yeah. Yeah, web frame. Yeah. So ship structure, you have web frame to support the twisting stiffness. This doesn't have this trapezoidal all the way, right? Since to deal with the nuclear, you cannot change anything easily. So this is that's why there's a congressional hearing back then. There's a lot of issues today still. Those power plants not finished yet. So in the end, we had to get a multiple company involved, get a certified, say we can use. If you don't have this, if you have such a bad design, how we can mitigate based on 5S principle? That means we don't have stability, we don't have supportability, we don't have symmetry, then we need to have support, right? We have to provide the support. So actually this one is one, after first iteration, we put an angle, stainless steel, attached locally every 2 feet into the screen. And here's you can see how sausage get made. This is my note. When they send this to me, say we need another support. We put everything together. This is what I shared with you, and this is what after. Okay. Actually, you don't need to do measurement between the two after this. Actually, back then we have national labs coming in, say we're going to do massive supercomputing. Okay. Doesn't matter what computing. If the design is bad, you will not be able to find a solution. Okay. So in the end, I was talking with some of the people on shop floor. What is that? That's a middle school triangle stability. Right. So we don't need this fancy. So what you do is this angle iron get welded. We develop qualification for tag weld. Later on, they can be knocked out. For this particular case, because it's going to be 70 feet in this direction, lack of stability. So in the end, we agreed, say this braces has to be stay on until going after side assembly. Then you knock it off, collect back to continue reuse. So that means when you look at the production flow or construction flow, only remove those tooling when stability established. So that means you have to have those things go with the component all the way, right? So again, with that, I'm not sure. Okay, just quickly switch gear a little bit, because usually when I do some of the international lectures, I start with this chart. I think we have to be more realistic. I think in this country, we had to start from very basic, okay? So then we can go advanced. So now, obviously, lightweight is very important, and multi-material lightweight is the most efficient lightweighting design concept we can introduce, because Detroit did a benchmark, say, if you use a super high strength, ultra high strength steel, you get a 13% weight reduction for body in white. If you introduce this design for the Magnon lead, it's a 43% reduction. That means multi-material offers the most effective reduction, weight reduction. So aerospace, the example is Boeing 787 and Airbus 450. They use different very clean joining technology, very expensive. Automotive cannot build this vehicle today, even though this design introduced 8 years ago, 7, 8 years ago. We cannot build today because we don't have a technology. Too expensive, right? I personally involved with the T-Craft program, and we look at titanium and different high strength steel, competing that with the aluminum version and also with the copper fiber composite version. Some of you are aware of it. That means the key thing is different color indicating different material in design. We can easily demonstrate the benefit, but the question is how to build it, right? So again, quickly, just some of the technology relevant to that. But this was really prepared to take on those multi-material structure. So we can look at without intermetallic formation, that proven by our MC square, very high definition TEM. So you indicate this with a diffraction indicating amorphous phase, atomic ATP experimentally observed at the nanoscale how the atom interrelate. Actually, no crystalline structure indicating no intermetallics. That's we call it special metal glass of the propulsion because of no grain boundary involved. And then another one is dealing with the plastic to metal direct joining. We can put by introduce localized pressure and temperature. That's a key. Even this morning I had a meeting with the LSA polymer chemistry professor. They were puzzled how this process would work. They're going to develop an experiment to observe. Under that pressure temperature condition, we can produce molecular level bonding, and that bond so strong interface, no micro mechanical interlocking. That means that superb strength has to be accounted for due to the presence of molecular level bonding. And then experimentally, we observed that particular aluminum carbon O bond. We can also prove that with the MD simulation, because we've been criticized. So your sample might be contaminated, or for some reason there's debris. So in the end, when you do MD model selectively, when needed, actually you can demonstrate 80% of the polymer, which is indicated here as PA66, reacted with aluminum atoms. There's no contamination in the model, right? So that's to prove that point. And lastly, just one quick example. Multi-material make manufacturing even more challenging, right? We have a lot of trouble with the same material welding, but actually offer more new opportunities. So here's the example. We can consider generically using fraction mechanics concept between material 1, material 2. Really doesn't matter if it's plastic or metal, metal to metal, metal to plastic, or plastic to plastic. We identified if you can manage to put a bond together nicely, like as I illustrated here, then we can easily debond and rebond them. That because now I have a clear defined interface to work with. Using fraction mechanics principle, we can demonstrate for the given two material combination. I want to use this condition to create the best strength, this condition to produce best structural strength under fatigue fracture loading condition. Use this condition, I can open it. I don't want my enemy to know it, right? So I can open it when needed, either repair or remanufacture. So with that in mind, that means we've got to design bond so effective, so efficiently. We don't want to overbond because later on you can debond, make it easier to debond. So we develop criteria for arbitrary combination material. If the nylon to aluminum, that's about the bonding width is about 5. If the aluminum to steel, based on this thickness ratio, it's about 3. we can demonstrate, give you the maximum strength. You don't want to overdo it, costly, add material, that's the environmental impact. You just want to do enough, right? So actually to make it debound, say anytime we want to open up like a battery packaging, battery pack. This is important, depends on their fluctual rigidity ratio, and the alpha can be rotated to this side, and then that provide a maximum driving force to open up a crack. And that mechanism should never be triggered during operation, during service, but only triggered by technician or when they want to open things up. So with that, the aluminum steel, we produce almost pristine bonding surface opening. That means almost immediately you can rebound them, rejoin them, reweld them as needed. If you use a tensile load, that's a simulating structural loading in service environment, you develop fracture on the steel side or on aluminum side, which is desirable, give you maximum energy absorption, also give you the best fatigue fracture resistance. Right? For plastic to metal, we can do the same thing. Keep in mind, this is supposed to be Michigan's block letter M. Okay. Obviously, our student rushing put something down there. Okay. Forget about the good looking. You put them together, produce very good bond. This is exactly the same sample as this one. Okay. Same type of sample. And then you can pop it open at a particular location based on the relative stiffness and the thickness combination, and that open up, and you just brush it a little bit, and then reload them. As long as we deal with thermoplastics, that process can repeat many, many times. So we try to understand the fundamental mechanism at play with the LSA chemistry professor. So with that, just quickly, I'm running out of time. I decided to keep my concluding remarks more generic. So I think my message is, we will talk about, construction 4.0. We'll emphasize computer power too much for the cyber aspects. And nothing can replace the underlying physics, mechanics. I think even though I showed some simple example, the underpinning is understanding that little bit physics. Understanding a little bit of physics doesn't mean you're going to make things complicated. If you fully understand things, you can make things much simpler. Right? And then with that, I frame everything under smart construction is a key enabler for dealing with some unprecedented marine structure related challenges. Commercial side, actually, my funding mostly from industry and rapidly adopting those technology. Doesn't mean they know everything, but they willing to invest, willing to try new things. And this part maybe not offering much. On government side, we have a problem. Okay, so that means this may not be the right format to address, but I want to point out, that means and more than just technical, also business model, how to invest. So again, I may have exceeded my time, but I may entertain some questions. Okay.
Thank you.
So you were talking about crack propagation at the interface between the two materials. What is the behavior of that crack propagation when it's still going along the interface? It's coming into the interface perpendicular.
Very good question. That's the trick, right? By definition, say if you want to reuse material, reuse a piece part, you want to have the crack propagation along the interface without damaging nearby material. If you want that joint to perform best under all kind of loading scenario, you want that crack to go into the material. Stay away from interface. Okay. So that case, that means you want to have this type of filler mode demonstrated. That only requires that this bonding width has to be properly sized. Today, everything's empirical, just because the stress knot is so complex, right? And also how to deal with defects. I'm not claiming we know everything, but I think this is a new concept we last couple of years we developed. So that means if you want to have a clean open up, you have to have a trigger in the design. So that case give you a clean interface. So that coming back here, when you are the OEM or, the regulator, you want to see this type of fracture under test, because that give you the best load capacity, right? And then say, if you, today, we want to make sure always this happen. So if you look at the battery, recently I look at also battery pack when you drive electric vehicle, they put a massive amount of adhesive everywhere, right? Because they are not sure how much needed. So what we are saying is, you have a minimum bonding length, taking into account some of the defects, some quality issues, add say 10%. That's all you need to take on the worst case scenario load. Anything more than that, add a cost, add inconvenience. Right? And then we can design a process. For example, this length is important. If it's too long, you're not going to open up effectively. It has to be sufficiently short. This is based on fracture mechanics principle, and so we can pop it open. I'm not sure if I answer your question.
That was, I think what I was more asking, but that was really interesting is, let's say there's a hole in material two that a crack is originating from, and then it's propagating from material two, material one. What happens at that interface?
That interface will be intact. So by design, you want to have that. If there's a failure, you want to have that failure because that gives you best load capacity. I think that's corresponding to this case. Because you may have a bubble, some defects, and you want to make sure the maximum minimum bonding length already accommodate that defects based on statistical analysis of the quality. And
Yeah,
makes sense like that.
Questions?
So how is 3D printing and those kind of processing methods used in your methodology?
I think just in the beginning chart, we look at this, that's how, I think, let me just quickly coming back to that front chart. Well, decide not to get into because that requires some pretty detailed discussions. 3D printing, if you deal with the metal, steel, plastics, I don't have much knowledge because mostly my professional life dealing with metals. 3D printing is nothing more than just what we call all weld metal construction. It is welding. It doesn't matter if it's powder bed process or wire feed. It is a welding. So this demonstrates that. So actually welding, you have the defects. 3D printing, this is a CT scan. Those colorful indications are cracks, porosity, shrinkage, or inclusions. In welding, we have a similar situation. That means a lot of the things I talked about can be directly applicable. And actually, I do have a DOE project supporting nuclear application, how to certify this type of components, right? And then other part in terms of reduced stress distortion, they already have the arrow indicated. Actually, recently we looked at multiple samples that's discussed in my 515 class, 515. Inside out deposition or scanning, doesn't matter what is going on in between, gave you best results in terms of dimension accuracy control. And we already heard about that word, inside out. So direct applicable, but there's some other issues, when we deal with the interpath interaction, but they are still very similar to welding.
Thank you.
Because I was just curious about, could you clarify how you establish the molecular bonding, like through what kind of process do you press them really hard so they contact very close? Or
You got to generate localize the keyword, localize the pressure and the temperature. The mechanism, because the material is incompatible, right? So chemists will look at what element available, their interaction to establish bonding characteristics. But they don't talk about even localized temperature. They don't talk about localized pressure. So this is by definition is a multidisciplinary problem. I shared the chart with some of the chemistry professors. They were puzzled, right? So I don't know the mechanism, the MD model indicating under that particular temperature pressure range. As long as you can achieve it, you do see 80% of the polymer reacted with the fluid. So I don't have a good answer. I have a couple of programs want to understand.
So my question was simple. I was wondering in lab, how did you actually achieve that?
Very simple. I think that's in the one chart I just go by pretty quickly. It is in our lab, but we could go the machine disassembly. We just use a CNC machine essentially. Okay, this is just cylindrical tooling, H15, H13. I think one of the still not here. It's very cheap. You just get this because if you deal with aluminum, you don't need a special alloy. You put this in tool holder, rotating and sliding. It can go to 5 meters per minute, pretty fast. But that's already satisfied our automotive requirement. So what it's doing is you're producing friction heat propagate to the interface, right? You can do laser if it's transparent. That would be laser coming from the transparent side. You can do induction, and you can tune the frequency so that the heated region on the interface. And this one produces a pattern, sort of like a friction stir, but in reality, it's not a friction stir welding because you don't do anything to the interface, but the heat get there. By definition, this little cylinder serves as also pressure containment, producing local pressure vessel effect. Okay. And then during that process, heating, pressurization, and then you finish welding. Very simple. Yeah. And you can use induction, other means, but you cannot put this into a furnace and then pressurize it because you violate the localize. Because you need the support. What happens if you heat it up? This plastic becomes so soft, it's just coming up. You need a surrounding support. This little flat surface tooling worked very well. We are in the process of understanding the chemistry, the chemistry process.
I have a question. You showed examples of the symmetry that was important in terms of the public. So is that something that, and they were all done as case studies? Somebody did something that was wrong and they said,
Yeah.
So is that something that can be automated as part of a design? To once you have the design, so it doesn't satisfy these. Or yeah, that's my thing.
Yeah, so I think the essential this chart. Okay. That means when we say design for production today is by experience, all people sitting together. Yeah. Doesn't have a quantity tool. So the idea is the reason I'm bringing this up is the Koreans, Northern European shipyards. When you give me a vessel design, what they do, they spend a lot of money, manpower, how to build it. And that's the time to introduce this. We are not changing the overall architecture. So you need a box beam, but how to make up that box beam, right? We talk about it, but we don't do it quantitatively. This requires quantitative measurement each step of the way. That because I think the government contractor, they believe this part, they cannot charge $2,000. Not a value added from that point of view. So we do, if anything, minimum. Managers, design engineer, everything, everybody sitting just like this room, comment on it, rather than rigorously establish how do I satisfy those criteria. And then also we do have, I think I mentioned to you, one discussion. Now, once we have this, we can implement it by using AI. AI to detect, that means you have to have recognized attributes, you have to detect the patterns. We had a reasonable success, so that could be a separate topic in the future. So.
And the thought I had is, do things change when surfaces are curved?
That complicated, right? So you do have a curved surface, then you need to have support. How Detroit do it? They talk about lime technology because you have to apply all of the contractor. They over 180 years, they already have a tooling. So what you do is that say a box curved beam has a support, unless they have a self stiffness, that means stability. So you have a tooling, you have a handling methodology developed empirically over many years. That's how automotive companies work. But for shipbuilding, you use pin jigs to support a curved surface. They never be effective, particularly these days we deal with high strength the thin gauge material. That means that part, we need to have a proper equipment. Called reconfigurable tooling, and that will help with the stability and mitigate the asymmetry.
And that's not being done.
Not done. I think they just use pin jigs, give you a closed surface. But those just not good enough. That means for the component, you need additional support, not just to have a, say, the passive support, you need active support. Just like what I showed, that elbow component, you need to have a temporary braces. But every now and then, our shipyards, they use temporary support, they call strong bags, that's randomly used. Only use when you see you cannot continue your work anymore. So you get a hydraulic system, pneumatic, and then push a beam into a place, give you support. There's no procedure. The only say sort of ad hoc type of implementation. I would not call it implementation, you improvise.
Can I maybe ask one question?
Okay, go.
Seems to me that joining steel and plastic opens up a lot of possibilities. Can you elaborate on what?
I think the, for military structures, yes, and Coast Guard is a, what is it? Free response cutter, that's a top structure is aluminum, that's the bottom is steel. So the connection based on explosive welding, they never been that reliable. So that's our application. Obviously, DDG 1000 original design has a aluminum superstructure, steel hull, and also move to consider composite, carbon fiber composite, and then you always deal with joining. Particularly for electronic system, power systems, you do need to have those multi-material, dissimilar material. Use the icon of the sea. One of the things killing them is a sun deck. They want to introduce polymer and steel, so that will minimum weight because the sun deck requirement for luxury suite. And so there's a lot of motivation. That's the commercial side of the application. So there are a lot of special applications. For Navy, Naval Air is very interested in fiber composite to metal. But right now they use glue, they use fastening, add a weight, add a procedure. And then when you do quality inspection, add a lot of complications.
Well, if there are any more questions, let's thank you, President. Thank you.